Yesterday you guys did this calorimetry lab where you had to measure the energy gained and lost by substances to figure out the specific heat of a metal, and then we compared that to the accepted value to see what happened. Okay, so just quick pre-lab questions, I'll run through these. What happens to an object's thermal energy when it is heated and when it is cooled? Well, when you heat something up, you're actually adding energy to it to make the particles go faster, spread out a little bit. So when you heat something up, it gains thermal energy. When you cool it down, of course, it's got to lose thermal energy. Those particles have to slow down, come together a little bit. Okay. If a hot piece of metal is placed in a bucket of cooler water, what happens to the temperature of each substance? Well, you guys know when you take something hot and drop it into something cold, the hot thing gives away its energy to the cool thing. So the hot thing cools down, the cool thing warms up. And that's because the energy is transferred out of the warm object and into the cooler substance. Okay. And that's basically conservation of energy. Okay. Heat flows from hot to cold. Alright, so then you set this all up, and a couple questions before you get started. When you add this hot metal sample to the calorimeter, the water's going to get warmer, and so is the inner cup. Okay, and we have to account for that because the water's not just isolated, it is touching the cup. There's some conduction that can happen. And we know this because energy from the warm metal sample is going to flow into the water, and from the water it'll also flow into the cup. Okay, and then the temperature of the metal sample, of course, is going to go down. As it's losing energy to the water in the cup, it's losing some heat, so its temperature goes down. And how do you think the change in temperature of the metal will compare to the change in temperature of the water? Generally speaking, water's got the highest specific heat of most substances, and not just a little bit higher, but a lot higher, right? Water's specific heat is around 4,180 joules, so we expect water to not change very much, but the metal sample is going to have a lower specific heat, probably less than 1,000 joules per kilogram degree Celsius, and it'll change a lot more. So we expect the metal to have a big temperature change, the water to have a smaller temperature change. Alright, so then we just had some procedural things, go through, find out some information. Now, I didn't do this, but I do have some information from one of the lab groups so that you guys can compare your numbers and see how you did, or, see if they're somewhat close. And they had 131 grams, or 131.6 grams of water. They had a 57 gram inner cup on their calorimeter, and their metal sample was 17.8 grams. Okay. The initial temperature should be the same for both the water and the calorimeter cup because you put the water and the cup together and the energy will flow back and forth between them until their temperatures balance. And from this group it was 20 degrees or 20.1 degrees Celsius. Okay. The metal sample was heated in boiling water, so it was 100 degrees Celsius. You mix the two together and it looks like their final temperature came to 22 degrees Celsius. Okay. And everything has the same final temperature, right? Because if anything was warmer, energy would still flow from one to the other and the temperature would still change. So the change in temperature, the water increased by 1.9 degrees. The calorimeter's cup increased by 1.9 degrees. And the metal sample decreased by 78 degrees. Okay? And why is this negative? Well, because it lost thermal energy. Its change in temperature is negative. Okay, so then it says calculate the change in temperature for the water. Well, I just did that, right? Final minus initial each time. This one should be negative. How do the changes in temperature compare? Well, 2 degrees to 78 degrees, they're really, really different. And the reason they're really, really different is because of this right here, but also because of the masses, right? We had more water and less metal, and the specific heat of water is also greater than that of the metal. So they're different because there's more mass of water for my group and because there is a greater change or a greater specific heat for water. So not only is it harder to change its temperature, there was more of it to change. And the energy transfer that took place, the metal, of course, transferred its energy to both the water and the inner calorimeter cup. Calculate the total heat absorbed by the calorimeter and the water. And so to do this, you do Q equals MC delta T. Okay, but you have to do it once for the water because the water gained energy, and you have to do it once for the calorimeter because the calorimeter gained energy. But we have to keep them separate because they have different masses and they have different specific heats. Okay, so first you find the heat gained by the water. Okay, I'm not going to do the math. And then you find the heat gained by the calorimeter, and then you add these up together, and that's the total heat gained by the water. Okay, now and the calorimeter. So this is the total heat that the calorimeter gained. Where did this heat come from? Well, it came from the metal sample. The metal sample gave this heat away. So what we can say is the heat gained here is the heat lost here. So we're going to take negative Q is equal to the mass of your metal sample times its specific heat, which you don't really know, times its change in temperature, which of course it was negative 78 degrees. Okay, and then you're going to do this math, and that's going to allow you to calculate the metal sample's specific heat. Okay, the last thing to do in this lab was to go ahead and see how does this value compare to the accepted value, right? So you look it up, and remember, to get a percent error, it's the measured value minus the accepted value divided by the accepted value, and then make it a percent. Okay, and it's absolute value because we don't care if you were a little high or a little low, times 100%. And this group that I have here, their data was good enough to get them within 8% error, which is all right. You know, if you have less than 10% error, you're doing all right. If you have less than 5% error, you're doing really, really good. If you have less than 20% error, well, that's acceptable. But more than that, and you're probably making some measuring mistakes somewhere. Okay. All right. Now, the underlying principle of calorimetry is, of course, that the heat gained by one substance is identically the heat lost by another. So, in a calorimeter, we cheat a little bit, and we say we have a good enough system, okay, that whatever's in this inner cup can't get out of it. There's no thermal energy lost to the surroundings. Nope. It hits this, stays in here, so no thermal energy is gained or lost. So the change in energy for a calorimeter is equal to 0. We only have what we put in there. Okay, and when that's the case, we can say that the energy gained by one substance, so let's say I put a block A in here and a block B in here, or there's a liquid A and a block B, or we have two substances in here. The energy gained or lost by A plus the energy gained or lost by B has to cancel each other out. It has to add up to 0. Whatever this one gains, this one loses. So the total energy change is 0. Okay? And so then, when it comes to doing these problems, that's basically what you deal with. You have MC delta T of the first one plus MC delta T of the second one plus MC delta T of the third one, fourth one, fifth one, whatever, however many things are in there, is going to equal 0. The trick to doing this is to make sure you do your delta T correctly. Delta T is always, always, always final temperature minus initial temperature. If you do it backwards, you'll end up with a negative when you shouldn't. And so MC delta T plus MC delta T equals 0. One will be negative and one will be positive. If you have multiple things, then you might have multiple negatives or positives. But you need a negative and a positive because something's got to gain and something's got to lose. Okay, and as an example, I asked you guys to do some problems on page 321, and I want to run through number 7 real quick. Okay, number 7, page 321, says you've got methanol. We've got 400 grams of methanol. Okay, and we had 400 grams water. And we're going to mix these two liquids together. The methanol starts at 16 degrees Celsius. The water starts at 85 degrees Celsius. And we're supposed to figure out what the final temperature is going to be, assuming no heat is gained or lost to or from the surroundings. So then we can just rely on our equation that says, well, the total energy change is 0 then. So 400 mass times specific heat of methanol, which I don't know, but I can look up in the book, is 2.45. Okay, and I converted that to joules per gram instead of joules per kilogram because I'm using grams for mass, times its change in temperature. This is its initial temperature. Its final temperature, I don't know. Right? That's what I'm trying to find. So I have T minus 16 plus water. Water, also 400 grams. Specific heat of water, I do know, is 4.18 joules per gram degrees Celsius times its change in temperature. This is its initial, so this is still T minus 85. Now if you look at this, we know the water is going to cool down. It's going to give some heat to the methanol. So this is going to end up being a negative temperature change. This is going to end up being a positive temperature change because it warms up. Okay, and so that's good because this whole thing has to equal 0. Now, be careful. When you do this, you don't drop a parenthesis or forget to distribute something because you are actually doing math, you have to follow the rules. So 400 times 2.45 is 980 times t minus 16, plus 400 times 4.18 is 1672 times t minus 85. Okay? Don't forget to distribute this 980 to both of these and this 1672 to both of these. So then you have 980t minus 16 times 980, I believe, is 156.80, plus 1672t minus 85 times 1672, which is 141,120, equals 0. Okay? Now, you have a t here, those add up. These two things can both go to the other side. You just got some algebra left to do. So you have 2652t equals 157,800, right? This plus this over here. Then divide, and you get t equals 59.5 degrees. Okay? Now, stop and make sure that that number makes sense. 59.5 degrees is between the two temperatures. So this one got warmer, this one got cooler, so that does make sense. It's also closer to water's temperature, which makes sense because water has a higher specific heat than methanol, so we expect water to change less than methanol. Okay? So stop, make sure your answer makes sense. This one does, so we probably did it right. Okay. If you have questions on that, let me know. There is a quiz today after you have everything worked out. So if you want to make sure you can work 6, 7, 8, and 9 on page 321, I can get you the solutions for that. Otherwise, the quiz is today. And then tomorrow we will start a look at the laws of thermodynamics and what happens in a phase change.